Hello, ladies and gentlemen. Welcome to Friday. A happy Friday to you guys. Um, First things first, you're probably wondering what we're going to do about that quiz. So I made it clear I'm not trying to kill you guys, and I noticed that not a lot of people did super good on the quiz. So what I'm going to do to remedy that is offer you an assignment over the weekend to make up for it. So you should still have access to view your results on the quiz if you go back to Quizalize. So what I'm offering you is if you go back through the quiz, for each problem you missed, work it out on a piece of paper and explain why you got it wrong. In other words, quiz corrections. If you can do that, and then send that to me by Sunday night, of correcting your quiz problems, and I'll be here to help if you need help understanding it. Then I will add points back to your grade. Um, the way I add points back is I usually add half of the points you missed back to the grade if you do corrections. So let's say you got a 50. Well, what's half of 50? 25. I'd add 25 points to your grade if you did your quiz corrections. If you got a 90, if you do quiz corrections, what's I, ugh. So um, we covered molarity, molality. We covered boiling point elevation and freezing point depression. Those are all things you'd see in a chemistry lab in college. And here's the second thing you're always going to see in at least one or two labs and one or two tests in chemistry. I remember specifically that on the final exam for chemistry, there were quite a few acid and base questions. So we're going to go through it. Now, this isn't going to be like acids are like orange juice and bases like soap. We're going to go a little more in depth. We're going to really explain the pH scale. It'll be some cool stuff. So I'm on page 408, and I'm going to be doing a highlight reel with the notes. Um, so the first thing I'd like to say is that we need to talk about the physical, physical properties of acids. So, what are things you notice about an acid? So, what are things you notice about an acid? So, first off, they're sour. An acid is usually sour. Think like an aspirin or an ibuprofen. If you've ever tasted it, it's got a really sour taste. That's because it's acidic. It's things that make you pucker, things that are really tart, like orange or lemon. Those are all high acidic. Um, Number two is this one's a little more scientific than sour. Um, some, in other words, not all, dissolve and conduct electricity. In other words, a liquid acid, some liquid acids, you can conduct electric currents through it, which is pretty cool. Um, and this is because they ionize when they break apart. And that positive charge and negative charge, those can carry bigger charges through the liquid, which is pretty darn nifty if you ask me. Now, we need to talk about some notation real quick before we get into bases. So, something we're going to be using is this, 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 and this. I don't know if you guys ever used these with Miss Moog, um, but what the S means in parentheses is that something is solid. If you have an L, it means it's liquid. If you have gas, it means it's gas. I meant to say G. Um, and if it's AQ, this means it's an aqueous solution, which is basically a fancier way of saying liquid. I can tell you right now, we're not really going to see that too much. Usually you'll have aqueous, but there's always the chance. Why these come in handy is when we write let's say like a stoichiometry problem. Um, let's say that when you add, no, we talked about this with the balloon example right before we went out. So if I have a balloon full of H2 gas, and then I burn the balloon, then all the oxygen in the air around the balloon is going to combine with the H2 in a fire explosion and create water vapor. So in other words, two gases, when they combined, became an aqueous solution. So this is why we need that notation. So in a chemical equation, you could see what turned into what. Is it all solid? Is it all gas? Is it all liquid? That's why that's important. Let me show you an example of when it's important. And this would be an example of acids ionizing, okay? So if we had magnesium as a solid, notice on the periodic table, magnesium is one column over, which means the charge would be +2. Notice we don't really have a positive charge on this magnesium. That's because it's solid. Solid elements usually don't have that charge problem. Magnesium as a solid plus two HCl's, and this one's aqueous. In other words, imagine you're putting a solid little block of magnesium into a jar of liquid hydrochloric acid. So what do you think might happen to the magnesium? Well, let's see what happens. What happens when you combine these things is you end up with aqueous magnesium. So in other words, it melted that sucker. Aqueous magnesium plus two aqueous chlorines in two little gas protons. You end up with two hydrogens. Now, when this magnesium turns from a solid into an aqueous solution, it actually gets its charge back. So the magnesium gets liquefied in the acid, and it becomes an aqueous solution, and the charge comes back. And then what happens is our acid breaks apart. When they ionize, this is what we mean. You end up separating these pieces and making high charge elements, high charged pieces out of the pieces that were together and happy. Okay, so let's talk about bases. So one more thing on this before we move on is there's a chemical property that's being shown in this equation that I want to give you a definition for. What's happening is acids react with metals. Magnesium combines with an acid. Acid reacts with metals to produce hydrogen gas and a salt. It reacts with it to create hydrogen gas and a salt. Now let's talk about bases. So physical properties of bases. And it makes my car shake is not a good answer. Physical properties of bases. So number one, it's bitter. We end up eating a lot more acid than we do base because very few people like the very basic flavor. It's very, very strong. Like imagine eating soap. That's sort of what bitterness feels like. It's very bad in very high quantities. A little bit of bitter is great. A lot of bitter is way too much. It's also slippery. Basically, if you can use the word to describe soap, you're probably also describing um, a base. Number two, um, awkwardly enough, it's the same as an acid. Some dissolve and conduct electricity because they ionize. Bases can do the exact same thing. Um, but there's one more we have and this one's more unique to bases. Um, a strong acid and strong base neutralize each other. In other words, they cancel each other out. If you have a super basic thing and a super acidic thing, and you really mix those things together well, it should end up being really neither too acidic nor too basic. It should end up somewhere in the middle. Um, and this reaction creates salt and water. In other words, if I were to show you if I were to show you two different equations, one of them is producing gas into salt, and one of them is creating water into salt, you would need to know, hint, hint, you would need to know identifying whether it's an acidic or a basic reaction. But you didn't hear that from me. Okay? So, physical properties of bases. Here's an example of that reaction. So if we had our good old friend aqueous hydrochloric acid, which, by the way, in a lab setting, you're going to use a whole lot in college. I don't think I think maybe had two experiments that didn't use that. And some of this. Let's just put these two things together. What are we going to get? If we combine these two pieces, right? If we have a strong acid and a strong base, then this is going to create some salt, aqueous, and water, liquid. Fantastic. So, strong acid, strong base react to create a salt and water. Fantastic. So, this is what that's talking about. So, in other words, if you saw one of these equations, if I were you, I'd know what to be looking for to figure out which one's which. Okay, on page 409, which ironically is a very basic solution, there's this little table of acids and bases. I'm going to be using some of these in your quizzes. I'm going to be using some of these in your homework assignments. So please make sure you know which ones are acids and which ones are bases. Please put this in your notes. I'm not going to waste your time and write it down on camera, but I would please ask you to. Okay. Okay, so we're getting into some weird territory here. So pay attention. On page 409 is where I'm starting. So there are three models, okay? There's the Arrhenius model, the Bronsted-Lowry model, and the Lewis model. What are these all, you ask? So these models are all different ways of describing acids and bases, okay? And these three folk decided that they were going to come up with their own ways to talk about it. Each way is going to be different in some key ways, so we need to be able to tell the difference between them. So, let's talk about the differences between them. And I've got to keep my own little sheet to keep these separate in my head. So, in an Arrhenius model, I'm going to have to use a normal pen today because there ain't no way I'm going to be able to fit all my stuff into into the space I have here. Here's my pen. So, in the Arrhenius model, you have two things. You've got an Arrhenius acid and an Arrhenius base. An Arrhenius acid, let me get a little closer. There we go. An Arrhenius acid ionizes to release a hydrogen into an aqueous solution. So imagine you have that container of hydrochloric acid, right? And we had our equation where it creates a hydrogen later. The hydrogen and the chlorine separated. That would be an Arrhenius acid. It lost a hydrogen and it released it out into the world. An Arrhenius base this ionizes as well to release hydroxide, which is OH minus, into the aqueous solution. So the acid releases an H, and the base releases an OH. So this is the way Mr. Arrhenius would describe these. In other words, what he looks at as an acid would be HCl, because that's going to lose an H. Maybe H2SO4. And what he'd look at as a base would be something like NaOH, or maybe aluminum OH3. So it's pretty obvious to tell which one would be an acid for him and which one would be a base. If it loses a hydrogen, it's got one to spare. If it loses an hydroxide, it has one to spare. So that's the Arrhenius model. The Bronsted-Lowry model. So in the Bronsted-Lowry model, this is where we start getting a little interesting. So in I'm going to call it a BL, a Bronsted-Lowry acid is one that donates a hydrogen, which is also just a proton. So a Bronsted-Lowry acid is one that donates a proton or a hydrogen. A Bronsted-Lowry base is one that accepts a proton. In other words, the Bronsted-Lowry model sees the acid as one that gives an H and the base one that takes an H. He looked at it as acids and bases are paired. And he called this conjugate pairs. I wish it was clearer on this camera. Anyway, conjugate pairs. So if an acid's giving and a base is receiving, those two things are paired together. They're connected. Now this is where we get a little funky. So an acid donates and a base accepts. That means an acid has to have something to give. Once we've had a reaction, you end up with something called a conjugate acid and a conjugate base. These are awkwardly kind of flipped in the definition. So a conjugate acid is the thing that got a hydrogen. And the conjugate base is the thing that lost a proton. In other words, once an acid gives up an H, it turns into a conjugate base. And once a base says, hey, I'm going to take your H, that means he becomes a conjugate acid. A way to think about this is the more H's you have, the more acidic you're going to be. And so by taking an H, you become an acid, or more acidic. And by losing an H, you become more basic. The more H's, the more acidic. So once you lose one of those, you become more basic. He gave us an example of what this looks like. That's super helpful in my opinion. I just hope I have enough room. Um, so he said you have HC2H3O2. Notice this H, that means it's probably going to be an acid. So HC2H3O2, and that's aqueous, plus H2O, aqueous. Okay, so these two things are being combined. Which one do you think's the acid and which one do you think's the base? Well, already I'm sorry, this is supposed to be L. So already I can tell you that this has an H out front. That H is just asking to get taken. So this one's going to be the acid, and this one's going to be the base. Now when these two things get shoved together, if the acid is the one that gives away an H, then when these two things react, we're going to end up with this thing is going to give its H to this thing. So once this thing gets an extra H, you end up with H3O. And now that it's got that extra H, it's going to have an extra positive charge. Plus, what does this thing look like without its little H? It's going to be C2H3O2. And since it lost something, it's going to be sad, and it's going to be negative. And that's going to be an aqueous as well. So since this thing got an extra H, it's going to be our conjugate acid. And since this thing lost an H, it's going to be a conjugate base. I'd look at the example in the book if I were you guys. It's super helpful. I'm going to box this in because it makes my OCD happy. I'd look at the example in the book, and you didn't really hear it from me, but I'd recommend that you guys know the difference between the Bronsted-Lowry acids and bases and what's going to be the conjugate acids and bases. Know which one's going to be which if you looked at a reaction. And if you Google that, you'll have roughly 3 million examples to look at on the internet. So I'd recommend looking in Google Images for Bronsted-Lowry reactions. You'll get some cool stuff. So last thing, let's talk about the Lewis model. So the last thing we'll talk about is the Lewis model. So, a Lewis acid and a Lewis base. So, a Lewis acid, this is when we get annoying, accepts a proton. The Lewis base donates. I'm sorry. The Lewis base donates a proton. This is where we get annoying. Look at a look at a Bronsted-Lowry model acid. It donates a proton. What is the Lewis acid? Accepts a proton. They're switched. So this is where we get a little tricky. So maybe flashcards would help for this one, keeping them straight. But the good news is that's as complicated as Lewis went. So how Lewis would draw this out is more in electron dot diagrams than in an equation. So let me show you guys the dot diagram. I found this one on Google Images. I think it's better than the books. If you want to look at the books, though, it's on page 411. So if you had a lonely little fluorine, just kind of drifting out in space, right? He's got a little negative charge on him. And then he meets, walking down the street, a boron trifluorine. Hey, that looks fun. And all the fluorines have the little pieces. It's great. So, these two people meet in the street, and they say, hey, you know what we should do? We should work together today. We should all join hands and create one big compound. So you end up with boron tetrafluoride. They all work together. So the question becomes, who lost, who gave up something, and who gained something? So boron here, it looks like he has an empty spot, doesn't it? He's got room to grow. This fluorine is kind of maxed out. This fluorine could stand to give something away, and this boron could stand to accept something. So that means that this fluorine right here is going to be our Lewis base. And that means that our boron trifluorine is going to be our Lewis acid. These things are going to join forces and create something else. That's as big as Lewis models go. There's a wonderful little table on page 412 that I'd recommend kind of writing down. It really concisely tells us what the differences between these three models are. And then it gives us a really cool diagram. So, your homework for the weekend. And again, I'm going to make this all due Sunday. That'll give everybody time to get this done. I would recommend doing it sooner rather than later, though, to make sure it's fresh in your head. So, on 16A, I'm going to write this down. Hang on. So, your 16A review questions. I like question 1. I like question 3. And I like question 4. So I'm only going to give you 3 questions, and then I have one request for you. Okay? On pages 413 through 415, they use this notation. 1.00 times 10 to the negative 7. And they use that to describe hydroxide, water, and H3O. What do the numbers mean? I would like you to look through those pages, look for what I'm talking about, the 1.00 times 10 to the negative 7, figure out what they mean, and then give me a 1 to 2 sentence description of what it means. So your homework is really 4 questions, 1, 2, and 3 on the section review, and then this question. I hope that this acid and base stuff is cool to you. It's very cool to me. I'm looking to do an experiment this chapter for you guys to do at home, so be looking out for that. That should be pretty awesome. But with that, I hope you guys have a lovely weekend. Bye.